Yeah, well, class. Okay, so we're going to talk about two-dimensional kinematics. So motion that occurs in a plane and typically not in a straight line. So what we're going to do is very similar to what we did in chapter 2. We start out by defining things like position, displacement, velocity, and acceleration. So, and of course, to describe location, position, we need a coordinate system, and this time we have an XY coordinate system. So let's say we have a point, like this object can move in this plane. Now, what we're doing, generalized, is very easy to 3 dimensions, but we're going to stick to 2. So we can identify the location of a particle, say it exists at some point, with coordinates x, y. So we define a position vector, which goes from the origin to that point. And we usually call that r for a radial vector. So I'm sure I'm going to erase this. Let's say this is just point A. And it's described by this radius vector. So again, if I give you that vector r, you know exactly where this object is. So position is defined by this radius vector r. Now, let's say it's at this point at a time t1. Let's call that r1. And that's at a time t1. And then some later point, it's at, say, point B. So it moves somehow. We don't care how. But it moved, say, along that weird path going from A to B. So we can draw a vector R2 to describe the location at time t2, which is point B. And then we want to define displacement, where in 1 dimension, we said like delta x. The displacement is just the final location minus the initial location. So we're going to do the same here. Displacement is delta r, that's a change in position, which by definition is r2 minus r1. And so this is a case of vector subtraction, which I kind of forgot to cover in the section on vectors. But the way vector subtraction is defined, like what that means, r2 minus r1, that's just defined. We have rules for vector addition and scalar multiplication. So formally it's defined this way. So R2, we're adding 2 vectors now. So we have to multiply one of them by -1 and then add them. So there's nothing really new with vector subtraction. But we do want to be able to do this graphically. So we have to talk about vector subtraction, how we can represent it graphically. So to start with, it's very important to be able to look at a vector diagram and see an equation. So for an example, let's say we have vectors that look like this. Say vectors A, B, and C. And ideally, maybe, if you can't do it now, you should be able to, once you master this, you should be able to look at this and immediately see an equation. That's where you want to get to. Just look at this and see an equation. And I can write down this way. You think just tip to tail addition. So think of displacement vectors. I'll just write down the equation represented by this graph. That's A plus B equals C. So again, tip to tail method. Add A and B. So you start here A brings you here, B brings you here. That's the same thing as C. They have the same starting and ending points. So if A and B represent displacement vectors, the combined result of A and B would start at this point and here. Same thing C does. So again, you should be able to look at an equation like, or look at a picture like this and just see an equation. So it's really, which of these two do you have to add to equal the third one? And vector subtraction is a little bit more difficult to visualize. Like, let's look at this one. Delta R equals R2 minus R1. So we've got two vectors, like say these two, R1 and R2. And we want to subtract those. So you could kind of do it formally. You could do R2 and then R1 would point. It would be exactly like this, except pointing in the opposite direction. So we could move that vector over here, pointing. Let me actually do it that way. So we have R1 and R2, like this. And minus R1 would look exactly like this, except it points in the opposite direction. So this would be minus R1. And then R2 minus R1, remember we're adding negative R1. So this would be delta R. So graphically, that's how we do it, but I don't like this method really. There's a better way to do it. No, we could move this vector over here, and that would be delta R as well. So just connecting the tips of these two vectors. But there's a much better way to do this, I think. For me, it's much easier to just look at vector addition. So if we add R1 to both sides, we have R1 plus delta R equals R2. So again, let me draw these two vectors. We have R1 and R2. And so we just have to write, we have to draw this vector delta R so that makes this equation true. And so R1 plus delta R, so delta R would have to look like that. And then we can see R1 plus delta R equals R2. So when you're subtracting vectors, if you draw the two vectors so that they're starting at they have a common origin, the tails of the vectors have a common origin, you just draw a line connecting the tips of the two vectors. And then all you have to do is figure out which direction the arrow has to point. And again, if you don't know, if it's not obvious what direction, just pick one. Like, say we picked this one. Say we just guessed and got it like this. Then the equation that we'd have here is R2 plus delta R equals R1. And if we solve for delta R, then we'd have R1 minus R2. That's not what we want. We wanted R2 minus R1. So we picked the wrong one, but it's obvious that that's wrong. Once you get this idea of graphical vector addition, when you can just look at the picture and write down an equation, it's clear you did it wrong, so then you just flip it. Another way to think of it is, remember displacement, it's like we started at A and ended at B. So remember the path is irrelevant. So the net result of this motion from A to B would be this. Okay, so yeah, vector subtraction. Very important because displacement is defined in terms of subtraction. And we're going to use displacement as a foundation for what comes next, which is velocity. And I'm going to make this a little shorter than in chapter 2. So for velocity, V average is just displacement over time, and the instantaneous velocity we take this limit that delta t goes to 0. And then acceleration, kind of same deal. So A is the average acceleration. Now you might see a notation for like an average value, like say average velocity. You know, a lot of times they'll do that, V with just a line over it to denote average. The reason I don't do that is because then when we get to, you know, average velocity, it gets a little cluttered. So I'd rather just write out with subscripts. So our average acceleration over some time interval would be delta V over delta T. So again, we have vector subtraction. We've got these two, you know, the velocity vector at time t1 and the velocity vector at time t2. We'd have to subtract those. And then, of course, the instantaneous acceleration. We take the limit that delta t goes to 0. Delta V over delta T. So basically, we're just kind of mirroring what we did in chapter 2, except we're dealing with vectors. And just like in chapter 2, we're going to restrict ourselves to the case of constant acceleration. And our goal is exactly the same. Given the initial position and velocity, and given a constant acceleration, our goal is to find the position and velocity as functions of time. So we're doing the same thing as in chapter 2. All right, so these are just the basic definitions. And let's get to the actual problem. And I'm only going to do half of this, because I think after that it'll hopefully be clear. But going back to one dimension, again, constant acceleration. So we derive these equations for constant acceleration. So what I want to do is let's do the same thing with 2 dimensions now. So we're going to start out saying that we know the acceleration. So this is just off to the side. We'll reference that later. So we have a constant acceleration. And just like before, the definition of acceleration, it involves this limit. But if over some time interval the acceleration is constant, we can get rid of that limit and just say A equals delta V over delta T. So this is exactly true if we have a constant acceleration. And we're basically going to follow what we did before. Let's multiply by delta T and kind of move it around a little bit. So delta V is equal to A delta T. And delta V, that's a change in velocity. So V2 minus V1. All right, so let's say that we have these 2 velocity vectors. So at t1 we have v1, at t2 we have v2. And to subtract them, let's kind of break them into components. So I think I'm going to do this to the side and then just kind of write the result over here just to make it flow a little better. But like v1, we can say that's v1x and v1y. And v2 has components we'll call v2x and v2y. And so delta v, when we subtract these, we have v2x minus v1x and v2y minus v1y. And so this is the change in the x position of the, or the x coordinates of velocity. So we can call this delta vx, delta vy. So again, kind of wanted to actually work that out instead of just going directly to it. So let's do that. So delta v, we have delta vx, comma, delta vy, and then the acceleration will have in components, we already used that. Let's get rid of it. Okay, and one more step. I'm going to distribute this delta t inside over scalar multiplication. Now I should point out that ultimately what we're going to do is we're going to be solving problems in two-dimensional kinematics, and you won't really even see much involving vectors. So this is kind of like the foundation of it. And so we're just kind of establishing a foundation. But when it comes to solving problems, you're not going to be doing this. Because this might look very new and confusing right now. But when it comes to solving problems, we're going to get to the result and form a procedure. So this is just justifying this procedure that we're doing. So anyways, we have two vectors that are equal to each other. And the only way two vectors are equal to each other if their corresponding components are equal. For example, if you have vector 1, 2, and say 2, 1, they have the same components, but they're in the wrong place. So these two vectors are not equal to each other. Like one of them would go over 1 and up 2. The other one goes over 2 and up 1. These are clearly different vectors. So in order for two vectors to be equal to each other, like we have here, we have to have this component equals this component, and this component equals that one. So the result is delta Vx is going to be equal to Ax delta t, and delta Vy is going to be equal to Ay delta t. So, so now we've got that result. And again, this is for some time interval. So let's pick our 2 points, just like we did before. Let's say t1 equals 0. Going to move that over a bit. Say t1 equals 0, and t2 is some arbitrary time t. Then v1, let's say v1x. Let's call that v not x, and v2x is just going to be Vx. So again, this is at some arbitrary time, so this is going to be the velocity, the x component of the velocity at time t. Okay, so if we do that, let's just look at this one. Delta Vx, that would be v2x minus Vx. So that would be Vx minus v not x, and that equals Ax times t. So it's Ax times delta t, but delta t is t minus 0, so just t. And if we just move that term over, what we get is Vx equals v not x plus Ax times t. And if we do the same thing for the y component, what we're going to get is Vy equals v not y plus Ay times t. Now, if you check your equation sheet, these equations are not on it. And there's a reason why. That'd be a waste of space. Why? Because these two equations, basically we have this equation, just one for each direction. So if we just look in the x direction, we have Vx as V naught x plus Ax, and time is just time. It doesn't have an x or y component. And we have a similar one for the y direction, Vy, V naught y, Ay times t. And so, yeah, remember our goal is to find the velocity as a function of time, and we just did that. And then the next goal is to find the position as a function of time, and I'm just going to skip that whole thing and say it's this. I'll write down the result. So let's write down the entire result. Okay. So, we're given, now I'm going to write this a little different. Like, we're given the initial position. That would be x naught and y naught. The initial velocity, v0x and v0y, and the acceleration, which has components ax and ay, which are constants. So given that, we want to find the position and velocity as functions of time, and I'm just going to write down the equations. Now again, I didn't derive these, but the reason why is the way vectors work, you kind of just look at each component separately. And so if we wanted to find x as a function of time, like x and y, so the position as a function of time, if you know both of these, you have the position vector. Basically what we would do, just like we finding the velocity equations, which I'll write down next, to find these equations, we follow the exact same steps as we did in chapter 2. And literally, we would just do the exact same thing to get position as well. So I don't want to go through all that algebra. So this is the result. And again, these are not on the equation sheet because you can so easily get them from here. So here's generally the velocity part. You can just put a subscript x everywhere that you can place one. Like for all the vectors, you'd put a subscript x. T is a scalar, so you don't do that. And then for the y component, you'd put a subscript y everywhere. Same thing here, except instead of like rx and r naught x, we just call them x and x naught. But yeah, then velocity, that's a vector, so we do v0x. And then here, for acceleration in the x direction, we just want the x component of the acceleration. And, same thing for y. Now, there's a really cool, maybe I'll just post this picture. I was looking around. I don't have the book with me. But there's a very nice demonstration of kind of vectors, like in the real world. And what they did is they had this black background, and they had, we actually have an apparatus like this on campus. It doesn't work nearly as well as a picture in the book because, well, we don't have really set up with a kind of a strobe light and a camera to take the pictures. But basically it's a device that has two balls on it, and there's like a movable plunger that goes through it. And so it's like a spring-loaded thing, so you can hit a button. All right, trying to think exactly how it works. But when you hit a button, one of the plunger goes through one of the balls. So when you hit a button, the plunger moves over, and that causes one of the balls to drop. And there's another one, so when the plunger moves over, it hits another ball. And so one of them falls straight down, and the other one is given a sideways velocity, and it also falls. And what they did is they had it set up like that, but they had like a strobe light camera. So they're recording it on a film, but it's a dark room, and there's a strobe light, so when it flashes, it takes a picture, and then it goes dark, and then it flashes again, and it takes a picture on the same film. So the result is something like this. The two balls are really like right next to each other. Like say here's the ground. And then, they drop, and then, this one falls. This one's going to follow a path like this because it was given a horizontal velocity and gravity is causing it to accelerate downwards. But the picture looks a lot like this. So I'm actually going to erase this. So this is like a real picture of two falling objects. And they both started falling at the same time. One was given a horizontal velocity, the other's falling straight down. But you can see they're always the same height above the ground. So the only difference between them is one of them was given a horizontal velocity. But again, look at the height above the ground. That'd be this equation y. So this one here has v0x. Let's say that's 2 meters per second. Doesn't matter, it's not 0. For this one, v0x equals 0. But if you look at the y component, v0x just doesn't show up here. The height above the ground, this v0x has nothing to do with the height above the ground. Also, if you gave this an acceleration in the x direction, that would also have nothing to do with the height above the ground. So the height above the ground is only determined by the y values, like the initial y coordinate, the initial velocity in the y direction, and the acceleration in the y direction. And so, it's what makes vectors so amazing what we do is we treat the x and y directions completely separate. I mean, they're connected by time, but we set it up. We treat them as just completely separate. Like what's going on in the x direction has nothing to do with what's going on in the y direction. And for a problem we're going to consider, that's true. I just want to be clear. Physically, what's going on in the x direction can definitely affect what's going on in the y direction. But, once for the problems we're going to deal with, we're going to be able to write down, ax and ay. We'll be able to, collect all this information. So it's possible that what's going on in the x direction could affect the acceleration in the y direction. So, we already know what the acceleration and the initial velocity and the initial position are in vector form. So, in that case, it's safe to say, we can just keep x's and y's completely separate. Okay. That's basically the idea behind two-dimensional kinematics, and then all we have to do is practice it. Actually, you know what? Just make sure I'm not forgetting anything. We're definitely going to do a problem about this. Oh yeah, we have to do two problems. So I think what I'm going to do is I'm going to stop this one here because we set up the foundation, and then we're going to do two problems. So that way just smaller pieces to look at. And later on, if you want to look at one of these problems, much easier to find. So I'll stop this one here and then just record 2 more videos.